oh, all right, so we're going to do a thin-walled pressure vessel problem here. We have a spherical vessel, and that makes it easy. Spherical vessel, and let's see here. We have the inner diameter of the sphere, which looks more like a hamburger, of 8 meters, I said. 8 meters, yeah, and the internal pressure of 2 megapascals. The diameter of each bolt, or diameter of bolts, is given to us that we can use as 25 millimeters, and then we have the allowable normal stress of the tank material is 150 megapascals, and the allowable normal stress of the bolt material is 250 megapascals. We want to find the minimum wall thickness and the number of bolts. And the thing that we have to remember about a spherical pressure vessel is that the state of stress is always the same all throughout, and this sigma is P R over, I believe, 2T is the stress. This is a state of stress on the wall of a spherical pressure vessel. Yes. Okay. It's like the cylindrical stress I'm sorry, it's like the longitudinal stress in a cylindrical pressure vessel, right there. And so let's go. Let's start with the stress in the wall. Okay, so really what I mean here is that if I were to look at any element in the wall due to the internal pressure, I get, PR over 2T. This is my state of stress at any point. Sigma, where sigma is PR over 2T here. And T is the thickness of the wall. R is the radius, okay, the radius of the sphere. So let's look at one. Let's look at one here. Let's look at wall of sphere. And that sphere wall, it's that the applied stress due to the internal pressure, sigma applied, is less than or equal to sigma allow of the wall. Okay, the wall material. And the applied stress is a result of a mechanics equation, which is PR over 2T less than or equal to sigma allow of the wall of the tank, which is 150 megapascals. And so we have all these other, so now we just have to solve for T, and that means that T is greater than or equal to PR, which was 2 megapascals, times the radius, which is 4 meters, divided by 2 times 150 megapascals. And that gives me 4 divided by 150 meters, which is, someone have a number real fast? 4 divided by 150? Okay, so 26, if you convert to millimeters, 26.67 millimeters. That was way too easy. Okay. But of course, it was easy only if you could recognize the design relationship right away, right? This basic design relationship. So that's T is great. So you would choose something like, if you're designing this, you would say maybe, use T equal to 28 millimeters or 30 millimeters or something that the manufacturer makes, right? Now for the bolts, when you make the bolt here, all the bolts are over here. So the bolts go around right here, connecting like two hemispheres. Is that right? 2 hemispheres? Yeah. 2 hemispheres together right here. Okay? So they're connected. So what we have is, if I look at the cross section of my sphere, so now I want to look at the bolts. So 2 connecting 2 hemispheres, right here. So if I look at my cross section, if I just look at a 2D cross section, I have, here's that lip, I have my hemisphere, here's the lip, and then I have another lip, and then another hemisphere, like this. Oops. Like this right here. And the bolts go across right here, all the way around. Okay? The bolts go across all the way around. And if I were to look at, let's say I look at one side of this, if I draw a free body diagram, so if I have, let's see here, like this, right here. And I have, here's that lip again, like this. And then the sphere coming like this, like that. Then I have an internal pressure here, and I'm going to draw a circle for that internal pressure, like this, acting on that surface of the cut. Okay? All the way around right here, like this. So there's going to be this surface, and this distance is a pressure P. Okay? And this is the diameter, the inner diameter, the I, of 8 meters. And I want to know how many bolts I need to do that, to make sure I hold this together within the allowable. So what I have is I have that the I'm going to start with the basic design relationship. I have the stress applied must be less than or equal to the stress allowed in a bolt. Okay, stress allowed in a bolt. And oh, you know, I don't like that. How about let's do this. Because the reason I don't like that is I can't include, when I do the stress, can I include the number of bolts? Huh. Let's see. Let's try another way. Let's say the force applied due to the pressure has to be less than or equal to the force allowed in the bolt, in one bolt, times the number of bolts. Okay? Right there. And so that means the force resultant of all this red stuff has to be equal to the force resultant, or tension. Oh, I should have drawn those arrows. I should have really drawn those arrows like right here. Okay? The force resultant of each of these individual bolts added up, which is, you know, all these bolts is N times the force in a bolt. Okay? And so here, that force applied is the pressure times the area. So that's just P times the area, which is pi di squared over 4, less than or equal to the force allowed in a bolt. The force allowed in a bolt is the normal stress, sigma allow in a bolt, times the area of a bolt, times the number of bolts. Okay. And now we can solve for, we know this is, what was it, 250 MPa. We know that this is pi over 4 times 25 millimeters squared. And then we know that the pressure is 2 megapascals. And the diameter is, I'll just use units of millimeters, 8,000 millimeters right there. And so if I doing this algebra, I would get, oh gosh, this would be N is greater than or equal to 2 megapascals times pi times 8,000 millimeters squared divided by 4 divided by 250 MPa divided by pi over 4. Hey, look at how that worked out. 25 millimeters squared. And so that cancels, the units cancels. Can someone give me a number for that? 819.2 bolts are required. So N has to be greater than 819.2 bolts. But you can't use 0.2 of a bolt, you know? So that means you would say use 820 bolts, right? Okay. And that